Okay, good afternoon and welcome to the first IMechE Design Challenge app help webinar. I'm Jelena Gacic, the operations manager of the, have I unmuted myself? Yes, I have. I should have checked that bit to begin with. I'm Jelena Gacic. I'm the operations manager of the education team at the IMechE, and I'm in charge of 4 of our 5 student challenges and the institution's educational outreach work. I'd like to start by thanking you for your patience and understanding whilst we have worked to develop and test the app. We appreciate that the process took a little bit longer than expected, but considering the continuously changing landscape around us, we hope that you'll be pleased with the results and the new tools we've been able to provide you. Before we begin, I'll start with a quick overview of the agenda, which will include an introduction to the IMechE volunteers behind the app, some of you who you can see on the screen, an overview of the app itself, before moving on to a demo, and finally the Q&A session. At this point, I would like to inform you that this session will be recorded. The recording's already started. The recording will be made available thereafter on demand for anyone who may have missed today's webinar or might find it useful to revisit it. I would ask that all attendees kindly mute their microphones and keep your videos off to improve the quality of the webinar, and that any questions be typed in the chat box. We will answer all questions at the end of the webinar in the dedicated Q&A session. Now to introduce Professor Tim Breaker, the head of the Design Challenge Technical Committee and one of the key members behind the app.
Thanks, Jelena. Crikey, this is a bit more formal than I was expecting. I thought I was just bowling up for a quick chat with everybody and show them the app. But very, very nicely done. Thanks. So I think the easiest way is just to quickly whiz through the documents that go with it, which will give you a bit of explanation for anybody who's wondering how it all works. And then I'll give you a live demo of the app in progress, and also show you how you can change the data input and so on. So can I have control of the can you give me the share of the screen, Jelena? Thanks. So okay, hopefully you can see my screen okay. This is, can someone just give me a yes or a no? Because it's a little bit, Teams doesn't give you a preview
yes.
of what.
Yes, we can see it, and
okay,
I appreciate good.
That. Yeah. We usually use Zoom. Teams doesn't let you see what you're showing everyone else, from what I can see. So let's begin with the user manual in that case. Hopefully you can all see that okay. So just to skip through the this document and explain the pertinent points as we go along. So what we've done, we've developed an app. It's, to start with, it's not the full all singing, all dancing that we're going to use in the final. The part of the reason for that is that if we unlocked everything at this stage, then it would really be possible for the bright minds that we've got doing this competition to start working out the mathematics behind what we're doing, and then they'd be able to start homing in on an optimum solution. So to avoid that happening, what we've done is we've given you a fixed distance, and as part of that, you can sort of change your own device parameters so that you can see how it reacts. But what it means is you can't go changing all of the distances and the elevation of the platform, the angle of the platform, to start really understanding everything that's going on behind the scenes. So on to the next one. This is what we've actually got in the app. So unfortunately, it does take a bit of time. I think hopefully you'll appreciate that to create something like this, you're kind of caught between doing something that's all singing, all dancing, and is absolutely amazing, but has the functionality that we need for what we're doing. I describe it later on that there's like the 80-20 law, that we're about 80% of the way there. But then to give it all the real niceties of allowing you to be able to input your own sort of vehicle so that you can see a visual representation of that, and to have all of the bells and whistles and things like play buttons and so on and so forth would take an inordinate amount of time. So we've sort of got to a point where it's functional. You can use it as a development tool if you like, but it's not as sophisticated and as beautifully developed as the sort of thing that these days we take for granted when we download something from an app store. So for that reason, what you'll see is just the same representation of a sort of generic device that we grabbed and put into the simulation. So it will represent the basic characteristics of your device and give you a representation. So we don't need everything like your full CAD model at this stage. We don't need your full sort of bill of materials, which will give us the part masses, so that we can check that during scrutineering of the actual competition. And as I say, it doesn't have the variable range, it doesn't have the variable lane angle. If you're confused as to what those means, just go back to the project specification and read through that, and also the COVID amendments. The reason that we put in the change in angle of the lane is because for a virtual competition, obviously we can't judge it on the accuracy to a bullseye on a target, because it's mathematical, so it doesn't replicate build quality, and really that's what the big variable is when we do it as a physical competition. So this is why we're doing the virtual competition based on the time taken and also a score for the amount of energy used. And we thought that by just putting a slight angle onto the lane for a couple of the heats will give us that added sort of variable that teams will have to work with to design against. Okay. Oh yeah, and of course, just at the bottom there, it would be possible to put in your mechanical measuring device, but I think that's where the huge variation across all the teams comes in. So that would be incredibly complex to put in. So we've had to leave that out at this stage. So how the app works, the visual that you've got there, it's really replicating a simple device, and it can either have two wheels or a single wheel on either the front or the rear axle. It relies on it being motor driven, is one of the important aspects. It may have gears between the motor and the wheels, that's absolutely fine, so we can compensate for that. And also we've tried to put in a bit of real life where it doesn't just slam into the wall and then reverse, although you can try doing that if you like, but you may get some, that's where it may become a little bit unstable. So it's driven by a sort of a physics model called Unity. And so what we've done is we've built a simple mathematical model of a device, and then that links into this much more powerful, it's actually devised for games development. So we can sort of stitch our simple mathematical model into a much more complicated physics model, and then it can replicate what's going on in reality. But as I say, that's why we've put things like a spring on the front and also a reverse switch. And I'll be able to show you in the demonstration that if you don't get the relationship between the spring and the switch right, you'll find that the device will either just hit the wall and stop, or it may not reach the reverse switch may not even reach the wall because maybe the spring's too stiff or the spring's too long. And that's what would happen in reality. So you'll be able to see that in action as well. So they're the main components. We've called the wheels that are attached to the motor the drive wheels. The wheels that are just freewheeling are called the coast wheels. Again, that's one of the things that took us a bit of discussion. What do we call each one? The drive wheels, the driven wheels, the free wheels. So we settle on drive and coast. You've got a spring or an impact attenuator, a reverse switch, and it's still relative to the datum pointer as you had with the physical device. So as I've spoken about, the impact attenuator is there to do a job. It just means that if you're designing your vehicle, you will need to be able to put a bit of reality to it. So what we don't want is just a theoretical spring. We've actually asked that you find something that is commercially available, and then we'd like to see the data sheet for that. The reverse switch, don't worry, you don't need to be giving us the details of that. That's really just about a physical position relative to the spring, so that it makes the model work. As I say, it is realistic enough that if you haven't got that relationship between spring and switch correct, then you may find that you'll get erratic behavior, or it will not, it won't actually go into its reverse mode. Obviously the device relies on running with a motor. There's only two characteristics that we need, which is the torque at 0 rotational speed and also the speed at 0 torque. A simple DC motor has pretty much a very simple straight line curve from those two fixed points, as shown in figure 2. So all we're asking is that you choose a motor that has those two figures. And if you are in a situation where you've selected a motor that doesn't have that information, then please select one that does. And we sort of advise that in real life you wouldn't really go designing a device like this without knowing what that motor characteristic actually is. Again, we've put the gearing in there, and there's just a simple example. It may be that you've got a gearbox on the nose of your motor. Just check whether the motor characteristics that's been given, it usually is just for the torque and the speed of the output shaft. So if that's connected directly to the wheels, you may not even need to worry about any of the gears. But just if you have built, I've seen quite a few devices with gears and gear trains built in. So this is just an example to show you how to do that gearing calculation, so that we know the number that we're going to input into the simulation. Similarly, we've got aerodynamic drag in the model. That's down to you to wonder. It's a very low speed device. It's got a very relatively small frontal area. But we have got the ability to put drag into the equation, if you like. So don't get too hung up about having to calculate your frontal areas to the sort of 0.1 of a square millimeter or something along those lines. You'll find that it doesn't hugely affect the result. Again, we sort of played around when we've been validating this, and if you make the front of your vehicle the size of a sort of a sail, then for sure your device will struggle to move down the track. But again, that just little section is just if you can find the projected area of your device, usually from a frontal image on a sort of from your CAD system, then you can work out the frontal area, and that's just a plugin. Again, that's quite a sophisticated shape with the little wing mirrors and all that sort of thing. It will be absolutely fine just say to sort of break those down into simple rectangular and triangular shapes, and just perhaps either ignore the wing mirrors or just make an approximation of the area of the wing mirrors in that particular case. So don't get too hung up on the frontal area, but at least try and put a representative value in there. Data input for the other features. So we've got some dimensions, and that diagram there just shows you. I'll just zoom in on that a little bit if I can. So that diagram there just shows you the characteristic dimensions that we need. So the spring position and the switch position, and the diameters of the drive wheels as well. By the way, when we're talking about the mass, I'll perhaps come back to this in a moment, but we need the total mass of your device as if it was sat on a set of weighing scales. But we will also need the mass of the individual wheels, just so that we can calculate the rotational inertia of the wheels as they're spinning. And then we can scroll down to the data input file. So relatively straightforward. As I say, the mass is the total mass of the device. If you picked it up and sat it on some scales, that's what you would read. Then we do need the drive wheel mass. So that will be the mass of a single wheel, and also the coast wheel mass, also the diameters. We've spoken about the motor, so the stall torque and the no load speed. I'd advise everybody to take note of the units that are in brackets highlighted in this file, because if you go input masses as grams or wheel diameters as millimeters, you're obviously going to be a factor of 1,000 out, and you'll get some strange things happening with the app. I think in that situation, everything's going to be either far heavier or things are going to be much bigger, and it's more than likely that your device will probably behave very erratically, or maybe not even get off the line. So the gear ratio, that is if you have got some gears in the system, so you do those calculations as shown just previously, and then you can work out a final ratio. Frontal areas for the aerodynamic drag. By the way, we have got a rolling resistance built into the model, so that's really just down to the mass of ultimately the mass of the device. The coefficient of rolling resistance is the same for everybody, but it will be beneficial if you can make your device lighter rather than heavier in terms of the rolling resistance and then the energy it's going to use. For your spring, you've got the spring length, which is from just end to end when it's just sat on a surface. So that's known as the free length, or the as we put in there, just the front spring length. The stiffness is something you'll be able to take from usually from the supplier data, so newtons per meter. And then you've got the spring position and the switch position. So that's all the data that you need. I've just noticed that looks like we've got a repeated dimension in there. So the front spring length and the spring length, they're both the same. So we might just look at tidying that file up. I'll check that after we've done this. I'll just whiz through this just to make sure there's nothing I've forgotten. Yeah, all happy with that. Okay, so once you've input the data, then we can run the file, and then I think that's what I'll go to and give you a demonstration of that. And then we've got results and analysis that we can just cover briefly as well. If you do get stuck, then there's a few FAQs there already. Come along to one of these webinars, and then if you're still really stuck, something really isn't working, then if you do a quick email that Jelena can pick up, and then we'll certainly do our best to try and help. It may be that you'll get into. We've had quite a few people had a play around trying to break this. Sort of me being one of the main ones. I sort of get called the digital sort of hooligan, because I like to try and break these sorts of things. So I think we've ironed out most sort of bugs, but there's nothing like giving it to users to start playing with and finding out where the limitations are. I would always suggest, though, the first thing is, if you find that your device goes falling off the lane, or sometimes it will actually sort of fly off into space and disappear into sort of infinity and beyond. If that happens, just go back to your input file and check what's going on with the units, and make sure you've not got anything sort of back to front, or factor of 1,000 out or something like that. So here we go. We've got this is the input file. Let's have a look. So front spring length 0.1. Okay, yeah, that looks like from that screenshot I did when we created the document, we've tidied up the input file, so there's only front spring length as a single input, which is good news. So we can ignore that little bit of confusion. I'll update the document though, just so that it's there. So we've got this data file here. Let's have a look at how we can then play with the the files that we've got. So what I've done is I've already I'm not going to bore you to tears by going through the quick start guide, because it's essentially 2 zip files. You extract those files to somewhere, and then you'll be able to start playing around with the app itself. There are 2 versions. There's one called data, and then there's another one called no data. Now the reason for that is that if you run the data version, you'll find that unless you've got a very high spec computer, it will run slowly. The reason that it runs slowly is that Unity is obviously designed for doing its job, and its job usually is not to be outputting data every time it does a calculation to an external file, which we then use in Excel to sort of plot the performance of the device. So what we do is we've done a no data version, and I suggest that you play around with that one to start with. You make sure that you are you're happy with what you see. It looks sort of like representative. The speed that it moves correctly, that it rebounds from the wall, and then it comes back to the target. And when you're happy with that, then I suggest that you run the data version, because then that will output the numbers into a format that you can open in Excel, and you can have a look at what is actually happening and do some plots. Okay, so we're going to look at the no data version. So I've got the input file. I'm not going to change anything for now. So all I do is I'm just going to, let's move that perhaps over there and bring that one across. Okay, so I'm just going to run the simulator, double click. First time you do it, you may get an error message saying it doesn't like it because it thinks it's something malicious. The quick start guides gives you instructions how to overcome that. And then you can run the device, and it will go to the wall and come back. Now, again, we have to, perhaps some of you, when you're designing yours physically, you might have clever strategies to compensate for the fact that the device will skid when it comes back to the target. All we can do is switch it off when it gets to that distance, and then just let it skid that final short distance. Again, if you look at the output files, you'll see that at that point it switches off, and there's no more energy being used at that time. Okay, so in terms of the sort of competitive element, you're not at a disadvantage for a great big long skid when your device stops if it's a very quick one. So don't worry about that side of things. Let me just run it again and just explain a little bit as it goes. So I'm going to start it again. If you look, what happens, there's a bit of sort of, to help with the graphics, the camera sort of pans around the device just to give you a view of it, just to, sort of a nice visual representation. But one of the other things that's happening is that as the device lands into this virtual world, it's actually stabilizing itself, because it is a sort of a true little physical model. It has some stiffness to it in the Z direction, so sort of the tires and so on. So it has to settle before we switch the motor on. So here we go. I'll double click, and then if you timed it, there's about a 2 second. Well, there's a 2 second gap from when it starts. The device lands into the virtual world, and then it settles. The camera comes round, and then it will start moving. So here we go. All right. So the clock would have started there, and that would be your 2 seconds, and there it goes. Back and forth. I've got into the habit of every time I run it, I just close the window, and then let's start having a look at what we might do for the. Let's start playing around. Let's make it a lot heavier. So I'm just using Control S to save the file, and then I'm going to run the simulator again, and then you'll probably see that visually it's going to look a little bit different. So can you see it's visually a lot slower because it's now 10 times the mass that it was. It struggles to return to where it came from, and hardly any skid when we turned off the motor. Next thing I'm going to show you is, I think the important ones are things like, let's look at let's change the gearing. Let's go back to, perhaps we just make it slightly heavier. So I'm going to do 0.4 mass. and one-to-one gearing. Just save that and rerun it. Okay, can you see it's just moving? It's quite a heavy device compared to the 0.1 that it had, but we've now the gearing is a tenth of what it was. This is down to the motor characteristic that we've chosen with that gear ratio. So you can see that it'd be very, very slow to complete that. Okay, so let's stop that and let's go down to the other extreme. So let's try a ratio of 50 and try running that. Okay, so now it has no problem moving, but again, it won't be top speed because we've got quite a high gear ratio involved with that. So let's have a look what we're going to do next. I'll turn that back down to 10. Now I'm going to play around. This time I'm going to change. Let's change the spring length. Okay, so I'm going to make the spring twice as long as it was. Save that. Let's make the device quite light as well. Save that, and then let's go again, and let's see what happens this time. Okay, so it's fairly quick. It's bounced back. Let's try. I'm now trying to think what I did to replicate it earlier. Let's make the spring longer. I want to show you what happens if you get the spring characteristics wrong. Oh, it's still coming back. Oh, I know what it is. Yeah, sorry. It's not that that's going to do it. Forgive me. It's going to be... If this doesn't work, I'll have to think. I tried it earlier just before. I can't remember what numbers I put in. I tried it just before we started the call. I can't remember what numbers I put in. There you go. So what's happened in that case is the spring is too long. So the spring hits, and then it's not hit the reverse switch because the spring is too long, and then it rebounds, but the motor is still in forward mode. So then it drives it back against the wall. So this is a nice example of a sort of a damped spring system. So it just oscillates until, if you actually looked at the data, this would still be trying to power it forward. But what we've got now is the motor torque will be exactly matching the spring resistance at whatever position it's got to. Also, just to mention, while we're sort of hovering on this camera position, you'll notice that there isn't actually visually a spring on the model, and that's because everybody's spring is going to be different. So just for this iteration, we've ignored it. When you get to the final, if you model a spring on the front of your device, then it will be visible. I think it might be a bit more complicated for us to actually make the spring compress, but we'll have a look at that and see what we can do as it hits the wall. But just in this case, it's there's a little bit of mathematics behind the scenes that just means that it's working physically in terms of a mathematical model, but just the visual doesn't exactly match because of we've omitted a spring and a switch and so on. Okay, so so there we go. Right, let's. What we do then is we go to the data build. And I wish that we could have, this could all be working beautifully for you, but we do need you to create another input file for the data build version. All right, so this is a good example. So if you look now, the one I'm moving, this is that's the data build version. Whoops, and the other one is the no data. So if we look at that, you'll find that some of the values won't. Oh, hang on, I've opened the wrong one, haven't I? Forgive me. Or was I running the other one anyway? So they should. What you've got to make sure is that you've got the same. You've got the same values. Good word of warning: best not to open it, even though it does open quite nicely in Excel, because it loses when you close it and try and run it again. If you save it, it won't keep all the formats. So so the main thing is that just make sure when you run the data version that you've got all of the values matched between no data and data before you go. So that's the one I was playing around with. Look, so if you look in this one, we've got the spring position of 0.3, and we were playing around with the spring position of 0.8. So before we ran that, we would need to change that to 0.8. I won't do it because I want to show you a set of data. So we're going to go back to this is the data version. When you run it, what you find is you get a data file. So export data, as you can see here, which is different. You won't have that file in the no data build. If I open Excel, and then if I browse to that folder, just bear with me. You need to change it to all file types. It's the first thing, and then you'll be able to open export data, and you need to make sure that you follow the instructions in the quick start guide. My data has headers. Click next. Make sure it's comma delimited, and then finish that. And what you'll find is you'll get a nice data file of the time, the energy used, the distance traveled, and the velocity at at each point. Two important things to explain. If I scroll down, you'll find that the time base is 0.05 seconds, by the way, but if you look, there's no energy being used until the 2-second point, which is when we switch on the motor. So if you want to do any data analysis, start from 2 seconds, and then take it from there. And then the other thing is, depending on how many runs you've done, just make sure that I think that's all one file. You have to watch out because it writes continuously to the same export data file. So what I would do in this case is I've done a run, and then you could either copy this one here. Look, we could either rename it, or we could send it to another location. So I might just call that export data 1, and then I could rerun the simulator, and it will create another export data for you. At the moment, I'm just in the habit, because I want to keep them. I just delete it, rerun the data version. And this time you'll see that it's going to be much slower, because it's writing every 0.05 of a second. It is writing, or 0.005 every 5 milliseconds. It's writing to that export data file. So there you go. We just created a new version, and again, you could open that. I don't think it's my job to show you how to use Excel and to start pulling out the graphs and so on. But what I suggest is that you set up a template, and then you just copy and paste new data into the template, so that it automatically generates the graphs for you, rather than having to set up new charts every time you get a data set. So there you go. I think that is that's the basics. Has anyone tried it? Has anyone unzipped it? Has anybody got any questions? It's what we like. Silence. Oh no, there's a hand. Go for it. Yes.
Hello.
Hi.
I have a few questions, but I do apologize if they are very basic. By the way, my name is Diogo, and I'm from Bournemouth University.
Hi, Diogo. Nice to meet you.
And nice to meet you too. And thank you very much for this, and congratulations for doing such a challenging. I think this was probably greater than the actually IMechE design challenge to come up with this software. So a few questions I've got. Is the CAD model from the students just for visuals in the context of the software?
It's going to do two things, because what if you think about it, when we've created something like that, there's nothing to stop somebody putting in 0.001 kilograms for the mass of the device, and then it'll use very little energy. So what we need to see is we're going to get the teams to submit the model in step format, and then what we'd like to see is an attempt at a bill of materials that puts the materials and a mass that goes with it, and perhaps the density. We'll give you a template for that, by the way. And then we'll just do a little spot check just to have a look at various elements of it, and just make sure we haven't got time to be checking the whole thing. And I think there has to be a bit of, in this instance, there has to be a bit of the spirit of the competition. You know, we can't get all F1 about it, and that was 0.00% outside the allowed limit, and so on. So we just have to. I think we have to go into this, if we're using the simulator for a regional final, with a spirit of the competition. And for sure, behind the scenes, there will be checks, and we'll probably, if we find that a team's, come on now, you're being a little bit, underestimating all of your masses, we'll just have a word and see if you can do something in a bit more realistic. Plus, as well, I think it's to be asking to be giving us the details for every last nut, bolt, fastener, so on and so forth. The reality is that industry, you would be doing that. And it's asking a lot at first year, but there's nothing like students to surprise us as to what they can actually achieve. So let's see what they come up with.
Yeah, absolutely. Thank you.
Okay.
I have a couple more questions. I'm not sure if I'm asking.
Yeah.
Well, can they use different CSV files for different distances, or are they supposed to use the same settings all the time, because it's the same vehicle?
Yeah, so we've locked the distance. Yeah, but I think that's a good idea. That what you could do is you could have a template of CSV files for the input, and then you could just rename it to be vehicle data 2 each time you want to run that one. That would be quite a nice way of doing it. Yeah.
Okay, just have one more question, but this is, I didn't understand very well the no data versus data. Sorry.
Yeah, no, sure.
Sorry about that.
Unfortunately, that's a bit of a sort of a nerdy computing thing, in that mine seems to behave itself quite nicely, which is usually when we try and run it on a presentation like this, it will be terrible, and it'd be really laggy and stuttering. And that's because not only is it working out what it's doing as Unity, it's also spitting out every single number to that export data file as it's doing that, and it's spitting the data out that really slows it down, writing to the hard drive. So
I got it.
So we worked out, let's bin that when people are just playing around and developing it and seeing how quickly their device, and does it actually work, and does it actually move and hit the wall and so on. Because what you don't want to do is have to sit there for 30 seconds for every single run when it's not working.
So I got it. So it's just about saving the export file.
Yeah,
to the hard.
Yeah.
Okay, all right. Thank you very much. Thank you, Tim.
No problem. Okay, all right. Good. Happy to hear from any others. And I think as well, if anyone wants any help with things like sort of when we get towards a regional final, creating the bill of materials, what we'll do is we'll do a template, so it's just something that you can fill in as you go. Just give us a shout if that's proving to be difficult, and we'll be more than happy to help.
Hi.
Hi.
Thank you for the presentation. I have some questions. Do you prefer I speak to you or I type them in the chat? Which one is more comfortable for you?
I'm old school. I'd love to everyone to meet in person. If we can't do that, then we yeah. Text is I'm a slow reader.
No
So,
worries, no worries.
yeah.
I have a lot of questions. I hope that's okay.
Yeah.
The first thing is, where do we get the app in this document? We haven't received any of these resources.
Okay. I think has that just appeared in the chat? I've just seen a link appear on my screen. Yeah, Yelena, can you put the link into the chat if that wasn't it?
Sure, I can put it in. It would have been emailed around, and it's available. Both of the documents are on the website, have been sent to all participants, and the link is I think it's in the manual, because we specifically did that so that everyone would read the manual.
Okay. All right.
I just pasted the website in the chat. I think you can get all the information there.
Yeah, I've seen that. Thank you so much, Diego.
That's great.
The next question I have is, you mentioned the components in the device, including things like the spring. Is that necessary? What if the model we have created doesn't necessarily have that kind of spring?
Sure. Can I ask have you actually got something that acts as an impact attenuator, or
yeah, so we're using something like a limit switch.
Okay, yeah,
rather than a full-blown spring and whatnot. So that's what we were using, but
sure.
we modify our design to suit this.
I think you'll probably it will. I actually tried it earlier without the spring being active, and it will still work. When we were developing it, we did have it where it I can't remember what sort of speed and torque and mass we had, but we did create a situation where when it didn't have a spring, it would hit the wall, and then you would get a bit of a sort of a sideways component in the because it's basically just a mathematical model, and it did then veer off a little bit to one side and fell off the lane when it was on sort of the a 4 meter distance.
I see.
So which is actually quite nice, because then it is replicating a little bit what can happen in real life, that if you build a device and it just slams into the wall, there is a risk that it will be a little bit unstable, because it's going to sort of hit a switch just as a point, and then that you don't know which way it's going to sort of settle. If it did hit at high speed, again, if you do your device that it's going at a nice steady speed, then the chances are in reality it would just hit the wall, it wouldn't unsettle, it would trigger the switch to reverse, and then it would come back. So I think what I'm saying is, if you want to say no spring, then you can find a way around that for sure. All
right. The next question I had was about the change in lane angle. Which angle are you referring to in particular? Is that in the document? If it is,
sure. Yeah, let me I'll just point you in the right direction for that, because that's we did some amendments for COVID-19, because we did, I think it was sort of around September when we released this, or when we were writing it, and we did sort of I've been working sort of quite closely with the on sort of COVID projects, and people who had better crystal balls than me were sort of saying that we ought to have a contingency. So that's what we did. Like, let me just show you. There we go. If you see there, so this is a document that's called COVID-19 amendments, yes. And it talks about the simulator being one of the options for a regional final, and then what we're saying is that the lane could be plus or minus 10 degrees.
Okay.
Okay. Which again, in itself is quite fun for us developing the app. It was we wish we'd never said that, because it then means that if a device gets into freewheel, it will just keep running. Say you've got the lane pointing upwards, so the wall is at the high point. Even though you switch the motor off, the device just keeps rolling and disappears. So we had to do a bit of bit of thinking how to stop it doing that.
Yeah. Okay. And And then my next question is about is there any need to include any code? No code needed.
No code, nothing from your side. Just fill in that data file, and that's all you need.
So now we don't need to think about how exactly we're going to make the device go back and forth. That's already integrated into the app.
That's it. Yeah.
I
so
see.
you just put in your motor characteristic and obviously the mass, the physical data that we need, and then that's it. It's doing all of that for you.
Okay.
Yeah.
And my final question is that, just to be clear, any simulations that we make within the app visible to anyone else, or it's something we can keep iterating without worrying about
That's right. Yeah.
how silly we look. Okay, great.
Yeah, that's it. Don't worry, no one else is going to be able to see.
Okay.
I think it's also worth me saying at this point as well. Some of you will know me from being from UCL, and it's meant I've signed a disclaimer with the IMechE, so that we will see some of the data files, but they're not going to get handed on in any way. And I think that's really important as well, that no, it's not like some sort of open source platform where everyone's going to be seeing everybody else's data files. It's resident locally on your machine, and that's it. No one else can see what's going on.
Okay. Oh, I actually have one more question. When you said that the total mass is the total mass of the device, including the wheels.
Yep, that's it. Yeah.
Okay.
Yeah.
So the wheel. Oh, go ahead.
So yeah, the total mass is exactly like you pick it up and you put it onto some weighing scales, and then whatever that reads, that is your total mass.
Okay.
Then because the wheels spin, they have an inertia. So you imagine if you had really big heavy wheels and a small motor, it's going to take quite a bit of effort for that little motor to start accelerating those wheels. So we just need to know the wheel mass so that we can do the calculation for the inertia of the wheel as it's spinning, so that we can put that into the physics model.
All right. And sorry, this is my last question.
That's fine. Keep going.
When can we expect the final version of the app? Is there a tentative date?
We're going to give you the final version of the app at the final. That's the point. Yeah. So beyond this and the final, if you want to then you'll have data files that you can look at for the fixed distance and horizontal. Then I think what we're saying is use a bit of the sort of engineering education that you're picking up this year, and then see if you can work out how it's going to influence whether it's climbing up to the wall and coming back, or it's downhill to the wall and coming back, or what it's going to do over the longer distances. Okay, so you'll perhaps be able, from what we've given you already in 1.5 meters, at least you'll be able to work out things like how quickly your device will accelerate and reach its peak velocity, and then from that you'll be able to start working out the time and that sort of thing. Okay.
I see. Okay. Thank you very much.
No problem. And again, just to reiterate, so we're not releasing the final app until the final, because I know what would happen. Everyone would just really start working out what goes on with it, and you begin. We'd then start to see some incredibly competitive devices over every single distance. Okay, good. Any happy to take any further questions. There are any on the chat? Don't think there's anything we've missed. Anything you can think of, Jelena?
No, I think you gave a great overview. Hopefully everybody found it useful. It was very detailed, many parts very engineering focused, hence the whole point of this. Yeah. So if anybody else has any other questions, including general questions about the regional finals or anything else we plan to do, please go ahead and ask now or email me, whatever is your preference.
That's good. Two things I just want to say. I'm sorry it took so long. I wished it would have been quicker than it was, but when you sort of got everything else, I think we all know, for any of us that are teaching online takes an awful lot of time. So that's one thing. And I apologise. I never realised that some universities were actually going to build it into their assessment and coursework, which is the thing that certainly caught me out. So I'm sorry that if that caused some of you some extra grief. It wasn't intentional. We were just trying to fit this in around everything else that's been going on.
I think from our perspective and the IMechE's perspective, and I'm going to do this to everyone, I'm going to say thank you, Tim, for all the time and effort you've put into doing this, and we wouldn't be able to do it without you. So we appreciate your efforts, and I would like to recognise it in front of everybody. Thank you very much for everything that you do for the Design Challenge.
No problem. That's good. Also to say, if anyone's struggling with how do we get masses, densities, bills of materials, we don't know how to do a parts list, perhaps that's something we can cover in one of the next webinars to help, because I know that some of you will have done the Design Challenge more around sort of prototyping and learning how it works from that way, rather than doing it from a virtual perspective. So we're just trying to put something in here that means that we've got the ability to have a meaningful competition when we can't still be together. So please just let Jelena know, and we'll run a session perhaps in the next one or the one after that, where we'll talk about how to fill in the bill of materials, and contact us offline as well if you're really stuck. I wouldn't like to see anyone really struggling with it, because it's not the sort of usual thing that you do. We're here to try and help. How can you contact us if the design what's the email address? I should know these sorts of things.
That's fine. This is my bit. designchallenge@imechE.org. I'll put it in the chat as well if that's easier for you. Also, you have my direct email from the calendar invite, so any of these.
Yeah, it's in both documents as well, as is Jelena's. So talk to Jelena, and then it may be that if we get a collective of you that want some specific help, then we'll run a separate session to cope with that. Good. Spread the word as well. Let others know.
Okay. If nobody has any other questions, thank you very much for coming today. Thank you, Tim, again. Please feel free to get in touch. If you find it useful to join the next help webinar, because I'm sure we'll have different questions, please join us again. And thank you very much for your interest in the Design Challenge, for your patience this year, and for continuing to support us and the students through this special time we're going through.